Welcome back. In this session, we'll learn how to build an FM modulation in Simulink. Let's start. Now, first, let's have a look what's an FM. Now, we know if a message signal is given by AM cos omega mt, where AM is the amplitude of the message signal, omega m is the frequency of the message signal in radians per second. Same way, the carrier signal is represented by AC cos omega c t, where AC is the amplitude of the carrier wave and omega c is the frequency of the carrier wave in radians per second. Then the FM signal is given by this. Then the FM signal is given by this AC cos omega ct plus beta cos omega mt, where beta is the modulation index. Now what we are going to do, we are going to obtain first this theta. Theta in MATLAB. Theta. So how do we build first this beta in MATLAB? Let's start with this part, then add this in MATLAB. Now remember to have the frequency, instantaneous frequency. This is the instantaneous frequency. We know it's given by, you can write also omega instead of this. Omega, this is the, and if you differentiate this with omega c beta, sorry, this is the differentiation of this, and then differentiation of this part. Let me write it like this. Let me write it this by c dt of whatever is called. So this is how the frequency and phase are related to each other. So you can write either the values in frequency directly first, obtain the frequency, then if you write this equation, then integrate this, you get phase. That's what we are going to do here. Let me, to illustrate this, let me switch to MATLAB. So this is MATLAB. So let me open Simulink. You can type Simulink R. You can see this window pops up and you can click on the library browser, and then this pops up. Now again, you don't need to build these systems. These are already available to you in MATLAB. You don't need to do, and you can see FM modulator and demodulator are already available in Simulink. But we are just learning this how to use Simulink, so that's why we are trying to build this. All right. Now let me start with the sinusoidal source. Now this time I'm not going to take this source. I'm not going to use this sine wave. I'm not going to take this wave. Instead, I'm going to take a sine wave from DSP block. So let's say this is the DSP block. So this is the DSP system toolbox. And then is the source. Here I have this, and you can add it to this. All right. Then next, what we are going to do, we are going to use a gain block. So this is the gain block. This will give us the beta. And then we are going to use a summer. Right. And then we are going to use an integrator. Again, we are not going to use this continuous integrator this time. We are going to use a discrete integrator. So this is a discrete integrator will be available to you in this discrete time integrator. This is the discrete time integrator. Then we are going to have the scope. So this is the scope that's available to us. And then we are going to use a trigonometric or math operations. I think there will be one trigonometric block here. This is the trigonometric function block, and we are going to add it. And let me switch to the model now and show you how to connect these. Right, so this is our sine block. This is our scope. This is our integrator. Sum block. This is our gain block, and this is our source. So this is our message. And let me first set the parameters of this. So let's suppose the frequency is 5. Let's suppose the phase offset is 2 in radians. And let's suppose the sampling time is 0.00001. And we can apply and hit OK. We'll have this. And then we connect to this. So this is beta. So let me call it beta. This is beta. And let me show you the FM equation again. So this is this part. So this gives me this part. Now what we are going to do, we are going to add this. Then after we do the addition of this, we are going to integrate it instead of differentiate from this equation. Then this. If we take integration of omega c, that will be omega cd. So first I'm going to add this. Then I'm going to integrate it. All right, so let me switch back to the screen. All right, so I need one more block. That's the constant block here. Let me add that. So I need one more. So that's the constant block. Constant block, where is that? This is the constant block. Add it to the model. And then switch back. Now this represents our omega c actually. This is our fc. This is our fc here. And this is our carrier frequency. And let's suppose the value we take as, let me use the value of this carrier frequency equal to, let's suppose the value of this carrier frequency is, let's suppose the value of carrier frequency is 150. Okay, this is just an example. All right, let me switch back. And beta we take as, let's suppose this is 100. So beta is 100. All right, so this is our carrier frequency. Then beta timers cos this. So we are going to pass this to an integrator. And after passing this to an integrator, we are going to multiply it by 2 pi to obtain the angle in radians. So this is 2 times pi. You can see the result. So this is 2 pi. This is actually angle or angle. And whatever is coming here, we are going to pass it through this block. We are going to pass it through this. And we take whatever value is coming, we take cos of that. And switch back. And this is right here. Then we take connected this. And we are going to check the message signal also. So let me change the number of inputs of this. Let's change it to 2. And then what we are going to have taking input as, first input is the message, second input is the FM. And let me run this. And I haven't set the, let me first set this, the integrator sample time 0.0001. Please remember it, I have set the integrator sampling time equal to 1. This is what I have set. I have set the gain equal to 1 and the integrator sample time is this. That's what I have changed it here. Okay, then I'm going to switch back to the model. So this is the model and let me run it. Let's run it now. And let's see the result. Double clicking on this. And first of all, let me change the simulation time here. And let's take it to 0.2. Let's suppose this is 0.2. And then this is 0.5. And let me show you the result. So this is our FM signal. Now you are seeing both on the same. So let me change the view. Let me change the view. So this is our message signal. This is our FM signal. This, so you can see as the amplitude of the signal is increases, the frequency of the FM signal increases. As the amplitude decreases, the frequency also decreases. So this is indeed FM modulation. So this is how we obtain the FM modulation in Simulink. I hope you understood the concept. You can change the value of the beta and see the change on the frequency accordingly. Have a look at that, change beta for different values and see the impact of this. All right, let me end this session here.